All right, well, just a couple of announcements here. We've just gone over the exam solution together. The next homework assignment having to do with break-even and payback analysis, that's due before class on Wednesday. So Wednesday of next week. We're going to go over some stuff related to break-even today. All right, so this is where we left off last time. We had just calculated for the in-class exercise the range of profitable demand, the optimal demand, and what we hadn't quite finished was the graph. Let's see, I'm pretty sure I saved the graph file. That's not it. Here we are, yeah. I wanted to just finalize how you can put together a graph of the revenue, the cost, and the profit. All right, so let me just delete this. We had already gone over how you can just choose some range of demand, and then you calculate the price that's based on that demand, and then the revenue, of course, is price times demand. That's how much money is coming in. Your income for the company is how many units you're selling and the selling price. And then the costs are the fixed cost plus the variable cost per unit times the number of units. So that's the total cost. And then the profit is simply revenue minus the cost. So let's do a graph looking at, so here insert, we'll do a chart that has scatter with smooth lines. Wow, it kind of just figured it out for us this time. It's amazing how sometimes it does that, sometimes it doesn't. I'm going to delete all these just so I can show you how we could manually select those. All right. So we want to select data, and we're going to add a series where our X value is the range of demand, and the Y value is the revenue. Okay, so here's the first part of that curve. You can see that it's going up and it's starting to come down again. And we talked about why revenue begins to decrease because you've lowered the price so much that now your revenue amount is suffering. So let's add some more data here. Add another series, this time X demand and Y values will be the cost. Okay. Now remember last time what we said was that where these two cross over defines the range of profitable demand. So where your revenue is above the cost. I guess maybe I should label these so that, let me go here to format. Oh, I know what I need to do. Select data. All right, yeah, I'll just rename this. Instead of series 1, this one was the revenue. Now it's calling that, and edit this so that this series is called the cost. All right, so now it's more obvious that the revenue is the blue line, the cost is the orange line, and we're profitable anytime the revenue is above the cost. And then the last thing that I'm going to include to this figure is adding profit. So let me type that in. The X will be the range of demand, and the Y will be these profits. Now it's going to go negative, and it's going to totally change the scaling of my graph. See how now my graph starts at 0 and it goes into the minus? I don't necessarily want to show all this area that's in the negative range. So if I right click on the vertical axis and go into format axis, then I can tell it what I want the bounds of the graph to be. And I want it to start at 0. Even though these calculations of the profit are negative, I'll have it start at 0, and that way the graph, I think, just looks better. See how now it's showing, here's the profits, and it's going from 0 up to, I can change the range just so that maybe the figure is bigger. Let me have it go from 0 to 50,000 rather than 60,000. All right. Oh, maybe 500,000. That's more like it. And then here I could change on the horizontal axis. It's starting at 0 and it's going to 6,000. Maybe just make it 5,000. And I ought to also put in a label. Let's see, where do I have it add that? Here. So let's add in the following axis titles. And then that's here where I can call it demand, number of units. And then we could change this one to be amount in terms of money. And then maybe I should also change these numbers to be formatted. I wonder if I can make this currency formatting. Number instead of general, currency. The advantage there is that then it puts the $ and the commas. It makes it a little bit easier to see, although I don't necessarily need to see the cents. So let me remove the decimal points. All right, so now I'm pretty happy with that figure. That's a good representation of that previous in-class exercise. All right, now we kind of have to rush at this point, 11:34. Let's talk a little bit more about costs. Think about what if you were in the business of making Twinkies, just junk food. You're making junk food. And so the fixed costs would be the things, as we talked about last time, that don't change based on the level of production. So if you're making 1,000 a day or 10,000 a day, you still experience the same rent. You still have to pay the salaried employees, the people whose pay is just based on how much per year and it's not an hourly wage. They get paid the same amount regardless of how much the production line is running. The computer systems, the equipment itself, all those things are fixed cost. But variable costs are the things that are directly affected by the number of units that are being produced. So if we're talking about the labor of the hourly employees, if you're running 2 shifts, then you're going to have more hourly labor costs than if you're just running a single shift per day. The materials themselves, like the plastic wrapper or the sugar or like the hydrogenated soybean oil or whatever, like the input ingredients that go into the snack, those are variable costs as well. I almost called it food, which wouldn't be quite right. All right, so here's a graph that shows the variable costs and the fixed costs. So the fixed costs is a horizontal line. The variable cost goes up, the number of units that you're selling multiplied by the variable cost per unit, and then the total is the sum of the two. So here in the graph that we made, we did that same thing. This column has the combined effect of the fixed cost and then the variable cost per unit multiplied by the number of units. So sometimes we have a nonlinear cost relationship. Now, what this means, this curved shape, is implying that the more units you make, your variable cost per unit is decreasing. So think about if you were making snacks. If you buy flour by the bag, like let's say you go to Dollar General and you buy it 1 pound at a time, the cost per pound is going to be very high. But then if you go to Walmart and buy a 25-pound bag of flour, the cost per pound is cheaper because you're buying in bulk. So there's reduced packaging costs, there's less overhead involved with the delivery to the store and so on. So just your cost per pound is lower. Now, if you're going to buy an entire rail car of flour, then your cost per pound would get even cheaper. So a lot of things get cheaper the more you buy. That bulk discount idea is what could cause a nonlinear cost relationship. The fixed costs don't change based on production, but your variable cost curve is flattening out simply because your cost per unit decreases the more you make. Now, this is zooming in on the portion of the graph that is here. This portion of the graph where we just barely start to see the revenue exceed the costs. So that's where we're at here, is that break point. And anything to the right of the break point is profitable because the revenue is above the cost. Anything to the left of that first break-even point is where you'd be losing money because the costs are above the revenue. So what's going on here is that transition to profitability. Now, if your variable costs are reduced, let's say that you can negotiate a discount with a supplier on the sugar that you need to buy. That's going to bring your cost per unit lower, so that flattens out the total cost curve. So this black line represents where your total cost curve used to be. And if you bring your costs lower, then what that means is that the break-even point moves to the left, which means simply you don't have to sell as many units to break even if your cost per unit is lower. So here our revenue curve stays the same, but it's just somehow we have reduced our cost per unit, and that shifts the break-even point to the left. All right. So this is one way that we're talking about break-even. The word break-even can be used in two different ways today. And the first way that we're talking about break-even is just we're comparing our revenues and our costs. So the word break-even can mean that now if you're beyond the break-even point, you're profitable because your revenues exceed your costs. But there's a different way that we can use the word break-even, and that is when we're comparing two different alternatives for something. Let's say that we're considering whether we should use a computer-controlled lathe or a manually controlled lathe. The manually controlled lathe, since it's not computerized, maybe it's cheaper to initially purchase it. So this alternative one you can think of as the manually operated equipment. It's cheap, its initial cost, the fixed cost is low, but the variable costs are high because there has to be a person there and the person's earning a salary. Whereas this alternative two, the computerized alternative, has a higher fixed cost but a lower variable cost. Have you heard that they might start making hamburgers with a robot? They're starting to, because wages have gone up so much and there's a worker shortage. There's more pressure than ever to develop a robot that can make a hamburger. But the problem is, and I think they've got them, but the robots are pretty expensive. Like to buy that robot and put it into place is more expensive than to train a worker. And so that's maybe another example that lines up like this. At a certain point, the robot becomes cheaper than the human worker. So the cheaper piece of equipment is what you would use if you have a low number of units that are being generated. But then once you get beyond this break-even point between alternatives, then it's cheaper to use alternative 2. So what this is just illustrating is that alternative 2 is more expensive at low units of production, but more expensive is alternative 1 once we get beyond that break-even point. So that's kind of what today's in-class exercise is focused on. Which alternative to select based on what level of production is being undertaken. All right, we've only got 8 minutes, and so rather than have you calculate this one, I'm just going to show you the answer. We're going to jump straight to the solution, and I'm going to talk through it. And hopefully you can just kind of understand the underlying rationale and all these calculations. So this is, option 1 is computerized, option 2 is manually controlled. So you could think of it as like a lathe that is milling metal parts. So the important thing is to understand that this option 1, because it's computerized, costs $2 million, whereas the manually controlled one has a lower first cost. And this computerized one, although it's more expensive, it lasts longer, and it has a salvage value. So when we compare it to this other one, the capital recovery is going to be different for each one of them. Remember, capital recovery is just the per year cost of owning the equipment when you take into account the initial purchase price and also the salvage value at the end. Okay, so let me pull up the solution to this one, and let's look at this first part of calculating the capital recovery. All right, so first cost, option 1 versus option 2. Now you can see the interest rate that's specified in this problem is 9%. Where does it say that? Here. Company which sets them are at 9%. So the first thing, calculate the capital recovery. So the way that I did that is I have my first cost, the number of years, and the salvage value. And so here in the capital recovery, I'm annualizing the difference between the purchase price and the salvage value. So you can see the inputs here are the interest rate goes into it, the number of periods, so it's 9% interest, and for option 1, 10 years. The initial purchase price was $2 million outflow, and then $150,000 inflow is my salvage value, and that goes into the future because that's at the end of the 10 years. And so what that means is that each year my capital recovery is $301,000 for option 1. Option 2 is a little bit lower because it's cheaper equipment, even though it doesn't last as long because of that lower initial purchase price. Option 2 has a lower capital recovery. All right, so we've done the capital recovery for both of these alternatives. Now this is saying for an expected output of 1,000 units per year, what's the total cost for each? So the cost is the labor cost and the equipment cost. In this example, those are the two things that tell you the cost. The fixed is the capital recovery, the variable is the labor. So one of the ways that these different options are different is that the computer-controlled equipment has lower labor costs. Maybe we can think of it as it just has a single operator, and although they're more highly trained, because there's just one person operating the computer-controlled equipment, it has lower labor cost than option 2. If it has more people who are running that machine, even though they maybe don't make as much as the computer-trained operator, the labor costs are higher. So output is faster on the computer-controlled equipment, 3 units per hour versus 2.4. So here in this spreadsheet, what I've done is I have said, let's just assume a certain number of units. I think in this part B, it says 1,000 units per year. So if I want to make 1,000 units per year, then it's going to take me 333 hours to do that work with option 1, because it specifies in the problem statement its productivity is 3 units per hour. So 1,000 units to make, then it's going to take us 333 hours, whereas this other equipment has only 2.4 units per hour. So this hours of operation identifies how many hours is required to operate the equipment. And so our cost is going to be related to that, because we know that the computer-controlled equipment is $180 per hour of operation compared to $195. So you can see here that the fixed costs, let me get rid of this. There, maybe trying to collapse the ribbon. I don't want to always show it. There. Now I've got more space. I can zoom in a bit. Okay, so capital recovery we talked about earlier. Now the variable costs is simply the labor costs multiplied by the number of hours that's being operated. So the total overall cost is this capital recovery cost plus the labor cost. So what I'll do is I'm going to send you by email the template file that you can use just to save you from having to label all these cells. I'll send you the template file and I'll also post it on Blackboard. And my suggestion is go through this example and see if you can answer, for example, which option is cheaper at 1,000 units. So which one has the lowest total cost for 1,000 units? What about for 3,000 units? So if I change this to be 3,000 units, see which one is bold right now? I set up a conditional formatting between the two so that when I have 3,000 units and this has the lower cost, it's the one that becomes bold. And just to remind you, if you want to do conditional formatting, you highlight the two cells and you do conditional formatting. Let me clear the existing rule that's there. You highlight it, conditional formatting, highlight. Let me do a new rule. Only the top or bottom ranked value. So I want it to be the top one, the one that has the highest number. That's the one. Oh, and I didn't actually tell it what to do. Let me edit that. Phooey. Clear format. All right, so highlight them, conditional formatting, the top one, and then it's here that I tell it what to do. So make it bold, and let's fill it in with a light yellow. All right. So now it'll make obvious which one is the largest number. And largest means least negative because these are costs. So the cheapest cost is the one that will be highlighted. Now, let me just tell you, the last part of this is using GoalSeek, what is the expected output that makes the two options equally expensive? So what that's saying is find out what is the number of units that makes these the same. So here is a cell where I'm calculating the difference between the two. So this one minus that one, I want to change around the output until the difference is 0. So data, what if analysis, GoalSeek. So set the difference to 0 by changing the output and let it go. And so it's going to find that 245 units is the one that will have the same cost. And that's the break-even point between alternatives. It's 11:50. I'm out of time. Hope you have a great weekend. Look for that email from me. I would really urge you to work through this spreadsheet and see if you can find that break-even point.